So for the 6.6 problems that accompany section 6.2, we're again going to be using the zero-factor theorem to solve these equations. So let's remember what the zero-factor theorem says. That the zero-factor theorem will only work when the factors are set equal to 0. And it also only works when they are factors. So it only works with multiplication. Not addition or subtraction. So it's called the zero-factor theorem because the factors have to equal 0 and they actually have to be factors. Factoring is referring to multiplication, not terms that are being added or subtracted. So to follow the zero-factor theorem here, it meets rule number 2, but it fails rule number 1 because we've got terms that are being added or subtracted to one another. They're not factors here. So the first thing we need to do is factor this quadratic. So I'm looking for factors of 6 that will add to a negative 5. So a negative 2 times a negative 3 will multiply together to give me a positive 6. And when I add negative 2 and negative 3, I'll get negative 5. So the factors I want to use to factor this quadratic are x minus 2 times x minus 3. And it is still equal to 0. So now we meet both of the requirements for applying the zero-factor theorem. I'll set each of those pieces equal, x minus 2 equals 0, and x minus 3 equals 0. Getting a little ahead of myself. Add a 2 to both sides, gives me x equals 2, or x equals 3. And checking that real quickly, if I square 2 and then subtract 5 times 2 and add 6, I get 4 minus 10 plus 6, which does in fact equal 0. 3 should also work. Let's make sure it does. If I take 3 and square it and subtract 5 times 3 and then add 6, I get 9 minus 15 plus 6 equals 0, and it's true. 9 minus 15 plus 6 does equal 0. Now let's look at another example. Here in example 2, we're failing both of our needs. Our equation is not set equal to 0, and we're dealing with subtraction instead of multiplication. So I need to do some rearranging to get this problem to work. I'm going to start by just moving the 24 to the other side, because we failed both of our requirements. X squared minus 5x minus 24 equals 0. And then I'm going to factor. And I'm looking for factors of negative 24 that when added together would equal a negative 5. So those two factors are going to be a 3 and an 8. And since I want my sum to be negative, I need to make my bigger number the negative 1. So multiplying 3 times 8, I would get 24. Since that's negative, it would be negative 24. And when I add 3 and negative 8, I get negative 5. It's already set equal to 0, so I have now corrected both requirements. Setting each side equal to 0, I'm going to get x equals negative 3 and x equals positive 8. If I square a negative 3, it would give me 9, and 9 plus negative 5 times negative 3, that's a positive 15, and 9 plus 15 is 24. 8 squared is 64, and 8 times 5 is a negative 40, and 64 minus 40 also equals 24. So both of those answers are working. Now look at this next one. We've got an x plus 3 and x plus 8. So looking at our two rules, we are working with factors, but they're not set equal to 0. So this one feels like, oh, I can just set this piece, and this piece equal to 0. That won't work. Watch out for ones like this. That x, if you move it to the other side, is going to get subtracted in order to set this equal to 0, not multiplied. You can't divide out the x or multiply the x by both sides to get it to go away. So the first line of this equation, in getting it set equal to 0, is going to make it x plus 3 times x plus 8 minus x is what equals 0. Now, I got it to pass the first rule. It's equal to 0, but now it's failing the second rule. I'm no longer dealing with factors because I've got a subtraction in here. So I'm going to have to go ahead and multiply out these two binomials, FOIL them, and incorporate this other x, and then refactor in order to get to the answer. So let's go ahead and do that. We've got an x squared plus 3x plus 8 more x is going to give us 11x's plus 24 minus an x. Now I can combine these two like terms, and I'll have x squared plus 10x plus 24 equals 0. And now I'm looking for factors of 24 that will add to 10. So refactoring, I'm going to get an x plus 4 and an x plus 6. There's 4 x's and 6 x's, that adds to 10, and 4 times 6 is a positive 24. Now I meet both conditions. I've got only factors on my left side, it's set equal to 0 on the right, so I'll set each one of those pieces equal to 0. And go ahead and solve them. I'm going to have x equals negative 4 and x equals negative 6. We've got one final example to look at in this section, and that is an x cubed plus 4x squared minus 12x equals 0. So notice that our power of x has gone up another step. So if linear equations, ones where x is to the power of 1, have one solution, and quadratic equations, equations where x is to a power of 2, have two solutions, and box these, how many solutions do you think an x to the power of 3 is going to have? If you guessed 3, you're correct. It can have up to 3 solutions. Wow. So, we're coming back to factoring again. Looking at these three terms, do you see that there is a greatest common factor of x? All three of these terms contain an x. So if I factor that x out, I'm going to be left with an x squared plus 4x minus 12. With that x out, I now have a quadratic that I can factor into two binomials. So I'll leave that first x on the outside and set up my binomial factoring here. And x times x, so I'm looking for multiples of negative 12 that will add to a positive 4. So if I multiply a 6 times a 2, that will give me 12. I need it to come out to a positive 4, so I want my 6 to be positive since it's the bigger number, and my 2 to be negative. A 6 plus a negative 2 are the factors of negative 12 that will give me a positive 4. Now in this equation, I have 3 different factors that all need to be set equal to 0. This x term, the x plus 6 term, and the x minus 2 term. So x equal to 0, I set it equal to 0, it gives me my first solution without having to do any extra algebra. When I set the x plus 6 equal to 0, I'm going to get x equals negative 6. And when I've set x minus 2 equal to 0, I'm going to get x equals 2. So that gives you a summary of the equations you'll need to solve the 6.6 problems that go along with section 6.2.